theory we went through so far from the morning about electrolyzer, some basics of power converter and control. So, and you have, I guess you have a good lunch. Just to avoid you don't sleep, so we'll have some hands-on modeling. And we'll have a break in between, after 1 hour a tea break, then another 1 hour we'll finish it. So basically, yesterday you learned about bit of fuel cell modeling. So, but he was, sub model, very simple model representation of a electrolyzer to a very complex model where you involve thermodynamics, electrochemical, all these things. So basically we'll go with static model, dynamic model, dynamic again electrical equivalent dynamic model, and in there are so many approximation in the model, and finally after going through all this, there will be a 46 kilowatt electrolyzer will build based on its electrochemical equivalent. So all of you will be developing the model with us. So make your laptop open and MATLAB open and with a Simulink file. Okay. So my student has built the model already as a library, but he will show you all the models, but with the time limit, only the final complex electrochemical model will build and show you here. Okay. And this model we are going to use it for tomorrow for a load for a DC-DC buck converter hands-on modeling. Okay. Okay, you can start.
So good afternoon everyone. Hello. Good afternoon everyone. So shall we start? So like in today's session, so as we know, when any product dissociates between two reactants or a reactant dissociates between two products, we have some change in energy. It may be positive or negative, it depends upon the type of reaction. So after that we will try to model this equation as a Gibbs energy G is equal to H minus T delta S. To more precise, if we want to calculate the change between Gibbs free energy, we can write this equation as this one. So here delta H represents the change in enthalpy, or delta G is Gibbs energy change, and T is temperature in Kelvin, and delta S entropy change. So here we have significance of each term. Already our expert has discussed about that. So now first of all we will try to calculate the standard reversible voltage, because in Nast equation we know that E is equal to E naught minus RT by ZF ln reaction quotient. So standard value we can calculate by this formula at a relatively high temperature. The base of calculating the high temperature and low temperature is our room temperature. If we are working on above room temperature, then we can say that it is a relatively high temperature. So we have this equation, V reversible is equal to delta G by ZF. At standard condition we have this value is equal to 1.229 volt. Here V reversible is equilibrium potential. At equilibrium potential no current takes place, or we can say that no current flow inside the electrolyzer. Here delta G gives free energy change, and Z is the number of electron transferred during that reaction, which is equal to 2.
Second, so in between if you have questions in any equations or value, you just raise your hand. We'll go slow by slow. Okay.
So here new terms is F. The F is Faraday constant. So using this value we can calculate the standard V reversible voltage, which is we are going to use in open circuit or reversible voltage while we have non-standard condition. So at non-standard condition, when we required V reversible voltage, we are taking the help of Nast equation. So as we know that delta G is equal to delta G naught plus RT ln reaction quotient, which is represented by Q here. So delta G naught is equal to this from our equation, and when we further modify this equation, we can get V open circuit or B reversible is equal to B reversible standard plus RT by ZF ln reaction quotient. Here reaction quotient is determined by this formula, because here we have partial pressure of hydrogen and partial pressure of O2 raised to power 1 by 2, because in reaction we have half number of oxygen molecule as compared to hydrogen and water. So that's why 1/2 terms is there. So this pH2 represents the partial pressure of water vapors. So by this formula, or we can say that this equation, we can calculate the reversible voltage, which we can using in our electrochemical model. So after calculating this reversible voltage, we are going to calculate activation potential. So to calculate the activation potential, the basic one is the Butler-Bolmer equation, which is the electrochemical equation. With the help of this equation, we are going to calculate our activation potential. So Butler-Bolmer equation represent I is equal to I naught e raised to power alpha A F V neta by RT. Here every term has its significance. I is our current density, which is ampere per centimeter square. Here we mistakenly put meter square, but it is in centimeter square. I naught is exchange current density, which is this one, and alpha A and alpha C are the anodic and cathodic transfer coefficients respectively, and V neta is the activation over potential. So now we require the value of this V neta. So that's why we simplify this equation, and after all we end with V neta anodic is equal to RT by alpha F sine hyperbolic inverse I by 2 I naught anodic charge transfer.
So I hope how we get into exponential to sine hyperbolic in the formula involved, right? Okay.
So similar calculation we will perform for cathode electrode, because as we all know that in electrolyzer we have two electrodes, one is for anode, one is cathode. So this will represent the anodic calculation, and similar way we can calculate for cathode also. So this formula represents the cathodic activation potential. So our total activation over potential is equal to V neta anodic over potential plus cathodic over potential. After that, over activation over potential, we will going to calculate concentration over potential. One thing, we doesn't take care for concentration over potential when we are working less than 3 ampere per centimeter square current density. Above that we have to taken care for this less than 3 ampere per centimeter, it is approximately negligible, so we can neglect that. So to calculate V concentration, we write the electrochemical reaction for a electrolyzer, which is given in this way. So we can split this reaction as oxidation and reduction reaction for anode and cathode respectively. So by this way, as we previously used the Nernst equation, now we are also using this equation again. So in such way, after performing these calculations, we get concentration potential in this way. So our concentration over potential is equal to V anode standard plus V cathode standard concentration potentials plus RT by ZF ln hydrogen concentration upon standard hydrogen concentration. Standard hydrogen concentration or nominal hydrogen concentration is calculated at standard temperature and pressures. But this H2, which is a calculated one, it can calculate any non-standard condition. So our standard at standard condition, V concentration anode and cathode is equal to 0, and below the 3 ampere per centimeter square current density, these terms are also has very less value, so we can easily neglect that. But when calculation our scenario change more than 3 ampere per centimeter square, then these terms have significant impact on our equations. So that's why we have to taken care for that also. So after that, our last potential is B ohmic. Actually B ohmic is the major potential, because our main electrolyzer losses are dependent upon that only. So B ohmic is equal to I cell dot R ohm. I cell is the current which is going to pass through electrolyzer, which is a very high current, because we want to operate our electrolyzer at a very high value. And here R ohm is the resistance of membrane. We can more precisely that resistance of membrane plus interface resistance. But in particular scenarios we neglect this term. Some literature propose that this is very less, so we can neglect them easily. But R membrane is a significant value, so we can calculate the R membrane or membrane resistance with the help of this formula, which is equal to delta upon A sigma. Here delta is the membrane thickness, and A is the area, and sigma is the conductivity. Like our expert also informed you that this sigma thickness is the main culprit behind the efficiency losses. If we want to get the maximum efficiency, then we have to taken care this thickness. In future research, scientists are working on that, so we can develop some models that somehow we can get membrane less electrolysis. So we can get minimum value for this, or so that our membrane resistance should decrease and our efficiency should increase. So these are the values which we are going to use in our modeling. So you can take screenshot for that. Yes, sir. This also? This is completed, sir. Shall I proceed? Yes. So this is the first electrical model for our proton exchange membrane electrolyzer. This is the static one. Why we called it static? Because in this model we are only considering the ohmic losses in it. But as we all know that in electrolyzer there is different types of things is there. But in this case we are only accounting the ohmic losses. So to account that ohmic losses we are putting the resistance here, and we have this potential DC voltage source as a reversible potential. So in this we are having V cell reversible voltage, like in standard conditions we have this equal to 1.377. So to make this model we are taking a reference of thesis which contains all that models. All the values are mentioned there. So this is the value for cell reversible voltage. So in this way we have cell reversible voltage in series with that ohmic resistance, and this is our controlled source, which is basically this whole basically representing the electrolyzer. This controlled voltage source is controlled by this cell reversible voltage and V ohmic. For static model we are controlling our voltage source with the help of these two, and we are giving the supply for it when we are using it as cell level. We are giving the supply across these two terminals, and here we are measuring the current for this. So shall I have to run? So this curve represents our power. You are able to see this step change. This is due to voltage change. Basically we are giving a step change in our voltage to make sure that our electrolyzer works properly. This is the step we are giving at 5 seconds. So basically this step is due to that. So here we are seeing that power is equal to 24, which is the results of V into I. This is the static model. So any doubt so far in this model? This is the basic one. If we want to make the same model for stack, then we have to change this reversible voltage for stack. In electrical model we can replace this thing and we able to get the stack model.
Yeah, so basically stack is a combination of cells. Depending upon how much voltage we want on our. Yeah, so if you are given a power rating of the electrolyzer and voltage rating, so you will decide how many number of cells, like for instance solar PV. So how many panels you connect in series and parallel to get to the correct DC output. Similarly here also you can do that, cells can be arranged in parallel or series or combination of both to reach to a stack level. That stack will be the equivalent voltage of cell level voltage. So here we are just considering the series connection of the cells. So total voltage will be number of cells into each cell voltage. That's how you need to just change to design a stack. Clear? Okay.
So next one is the first dynamic model for proton exchange membrane electrolyzer. Like in previous case, we didn't have this Barberg impedance. In that case, in this first dynamic model, we account the concentration activation losses as this much. So like in previous case, we didn't have this term. In first dynamic model, we introduced this extra term. Basically, this term is accounting the activation losses. In previous case, we consider only ohmic losses for our electrolyzer. But as we all know that only ohmic losses are not there, we have some another losses also, another terms also. So this one is the for activation over potential. So here we add one more resistance. The value of that resistance is equal to 0.05. It is also mentioned in that table or .im file we are using. This is the capacitance, because as we know that in electrolyzer it has double layer capacitance. Professor Jahangir also modeled that, he gave us a formula for calculating that, but here we are using the value for that. We are using 1.93 Faraday capacitance value here to model that double layer capacitance. So this represents our activation losses and this is our ohmic losses like previous one, and same manner this is our controlled voltage source, which is controlled by ohmic potential, cell reversible voltage, and now one more term is added here, that is activation potential. So this potential is controlled by this value, summation of these three. Now we can do this. Yes, sir.
Sir, on what basis that capacitor value is designed?
Actually, we have formula for that. I will show you. Yes.
It is RC parallel, so the equation is in terms of, I think, time constant and.
Yes, ma'am.
Huh.
So Barberg impedance, yes, ma'am.
Mm-hmm. Okay, sir. Thank you.
So you can see that this is how we are getting the value of voltage. Previously we are getting exact 24 volt, but in this case we are having this curve like that. Here we are using the saturation block to just show the good results, but due to that capacitance it has some this transient spike is there. This basically now our as you can see that our power value also decreased. Like in RC parallel circuits, our graph is like that. So it is representing the same circuit. So now next model, in previous case, we only consider the activation losses, but apart from activation losses we also have the concentration losses. So in this next dynamic model, basically it is derived from that model only. Here we are just using one more resistance to account the concentration losses also. So this whole circuit is similar with the previous one. Here we are having the activation resistance and here we are using the concentration resistance. With the help of these two, we are able to model the concentration and activation losses for electrolyzer. With the help of these three values, ohmic losses, activation losses and concentration losses, we are able to get control signal for our controlled voltage source, and across these two terminals we are giving the excitation to our electrolyzer. This is the cell model. If we want to create the stack model for this also, then we can just replace this value with the cell voltage value. Now I will show you waveforms. So now you can see that the results is little bit similar to previous one, but if you able to change that, previously our power is settling towards this much value, now it shifted somewhat upper than that. This is due to counting that concentration losses. So this is the counting concentration losses as a resistance only, but as we all know that we have two electrodes in our electrolyzer, so we have to make some arrangement so that our both electrode concentration losses should be accurately modeled. So to account that, we are using this next model. In this model we are accounting the concentration losses as a Barberg impedance. The meaning of Barberg impedance is a resistance connected with the parallel capacitance. So with the help of this, like in RC parallel circuit we have time constant is equal to RC. So this results in exponentially decaying curve. Apart from that, this is the ohmic losses. This resistance is considering the ohmic losses only. And this resistance is for activation losses, and these two resistance in parallel with the capacitor, or we can say that these two Barberg impedances represent the concentration over potential. This one is for anode, this is for cathode. Here we are modeling it as a single one, but in further derivative of this model we can model it as a different set of value. So now here also we having the 4 potentials to control that voltage signal. Here we are introducing one unit delay, because if we are using direct giving the direct value, then it may cause algebraic loop error in MATLAB, or in a practical scenario we can see that this capacitance doesn't allow the transient change in voltage or abrupt change in voltage. It has some it takes some time to get that value. So for that value, in practical scenario we use first order transfer function here, in which we can multiply the tau with s. Basically tau represents the RC. Here we are just giving the unit delay to account that losses. So this is our next and final model. So in this model, as you can see that we have all losses accounting separately. So this is our first ohmic losses, a resistance which is taken care for ohmic losses. This is the reversible cell potential, and this is basically capacitance connected with the parallel. This resistance is for activation losses, and these two Barberg impedances, which is for anode and cathode respectively. First we will taken care for anode, and next we will taken care for cathode. Similarly for activation potentials, because as we know that we have two different set of electrodes, so we can't activate both electrodes at the same time with the value have same potential value. So that's why we are trying to model it in a separate ways. So this circuit represents the modeling for that. This is basically for anode, this is for cathode, and here with the help of this voltmeter block, or we can say the voltage measurement block, we are getting the values, and by summing the two both activation potentials and concentration potentials and adding them up and give the control signal to this controlled voltage source, we are able to get the desired results. So this resistance is just representing the internal impedance of the voltage source, because no source has a ideal one, it has some drops across it. So that's why we are considering the very less value for it. So this one is the final dynamic model for cell. Now next one is the alkaline electrolyzer models. In morning session, Professor Jahangir described that our proton exchange electrolyzer is faster than alkaline electrolyzer. So the reason why proton exchange membrane electrolyzer is faster, the main reason behind that, this inductor. In alkaline electrolyzer, while we model it in electrical domain, we have this equivalent inductor here. to represent its opposing. While in case of proton electrolyzer, we didn't have this inductor. As we all know that inductor opposes the abrupt change in current. So when our current shifted to if anything happens inside the electrolyzer, then current inductor doesn't allow to abrupt change in the current. So that's why this inductor will cause the this inductor will increase the response time of alkaline electrolyzer. So if we want to see the response, we can check. So you can see response time is faster, more than proton exchange membrane electrolyzer. And one more thing, can anybody tell that this is the static model or dynamic model based upon the comparison with the previously?
Yes, so his question is it a dynamic or static model? Anyone? Students?
Here we have only ohmic losses. Ma'am, here we have only ohmic losses, so this is a static one. Yes, ma'am? Ma'am, this is for alkaline electrolyzer. Previously, we are discussing the proton exchange membrane electrolyzer. In this model, we didn't have inductor, but in alkaline electrolyzer, we have inductor in the circuit itself. So this is not representing any type of losses. It is an inbuilt. Yes, ma'am. So this is the static model for alkaline electrolyzer. So next is the first dynamic model. So here, like in previous one, we are counting the activation losses as a Barberg impedance. Like we did it for previous case, we have this capacitor and resistance, which is accounting the activation losses. So this is account the activation losses. All other things remain same. If we want to make equivalent circuit of proton exchange membrane electrolyzer with the help of alkaline electrolyzer, then we can do one thing. We have to just replace this inductor. Apart from that, everything is same in both the circuits. So this is the more detailed model for alkaline electrolyzer. Here we are modeling the anode and cathode losses differently in different cases. This is for activation potential for anode, this is for cathode respectively, and we are accounting these losses to give the control signal to our controlled voltage source. So we can discuss one stack model for this also. So previously we discussed the cell models for alkaline electrolyzer. So this is the stack model, because we can't give the too much higher value of voltage to a single cell. So we have to make some arrangements or number of cells in combination, so that we can able to give the supply of that much amount. So here we can, like in previous protonic exchange membrane case, we can just replace this V stack reversible voltage with this value for stack. Apart from that, resistance remains same in electrical modeling. This is the major drawback for this. While we are counting the electrochemical model or physics based model for we are particularly doing for proton exchange membrane electrolyzer, we taken care for these losses also, because while we have cell level calculation and stack level voltage, our resistance should not remain same. It has some changes. So now I can show you the power comparison. Is it visible to all? So here we can see that we have some different types of waveforms. These are basically representing the power in each case. So here the first, we can start with the yellow one. This is the static power. In next case, the blue one, you can see here. The second one is the dynamic power. Dynamic power in first case where we are accounting the activation losses only. So this is the that power, this blue one. It has some settling time, I think up to 0.4 second or 0.35 second. After that it is overlapping the value which is given in the static power load. And next is the dynamic power in PEM electrical model. The third case, which is shown by this orange curve. This has some drop because this is the electrochemical model. We are trying to model this after IIT session. So next is this violet curve. If you able to see, this has some more over spike, because when we are trying to model anode and cathode potentials different in two ways, then we have more capacitance value there. So which is results in the more RC value. So that's why more spike is there. Apart from that, these all values are settling after some time at same value. So shall I run for more time? Yes, sir.
So all this model we just give you a overview, which is basically the dynamic electrical model. But the next model what you will build with us, basically the electrochemical model, where we will build the equivalence or all the calculation involved in the electrochemical reactions also. So you will put the parameter file in one side and model in one side.
Yes,
so
sir.
you match this to this.
Yes, sir.
Okay, so all of you can see you have the parameter files with you, right? So now you open your MATLAB and just follow how we are doing here. It's a good exercise actually.
Yes, sir. Shall we start?
So we can open a blank MATLAB simulate page. Yeah, we will share, but you don't have MATLAB? No, we said that parameter they won't take. You are different for. Why don't you show the data? Zoom in.
Shall we share in group?
So we are sharing in the WhatsApp group for you.
Sir, group किसके पास? Group.
You are there, na? And go back to that PDF. We'll match the equation and build it parallelly with the Simulink. Okay.
So first of all, we required power GUI block to operate the power system library. So that's why we import that block in our model.
Somewhere regarding the model, raise your hand, will stop for you, okay?
So next we will start with the calculation of open circuit or reversible voltage. For that we have to model this equation. Shall I put in this way? I think it is more better. I think it is more better because if we no sir, so here we put the screenshot for the first equation. Now we are going to model it this equation. Just copy paste.
Yesterday you saw how you use .m file. The same .m file will use the mathematical operation using the block itself. So either you can use .m or you can use like this what you are doing now. So all these blocks, basically you have to take a constant block and a product block and a summation block. So with the help of that, you try to build this part first to calculate the concentration over potential, right?
No sir, this is the reversible or open circuit.
Open circuit voltage, which is basically, if you can see, it is independent of current. So this is the amount of potential required to start the electrolysis process.
Yes, sir.
So please try to build this.
So this equation basically represent this first term is the constant block. This one. This is for this V reversible standard value. We have this value in our .m file, which we can share with you in the form of screenshot if you want the reference. Yes sir.
Just now I shared a PDF in the group, so that is what this document is about. You can follow the equations from there. You put side by side.
Okay. So we are implementing this equation. This one. Control plus and the mouse.
Anyway, I have shared that. You just take the page number and please try to build this. We'll go forward then. That MATLAB you put in fit to zoom.
I think
bit
now
of
equation is visible.
that MATLAB also make a zooming. Is it visible? The MATLAB? Okay, try to build and use the same variables.
So basically this constant block is accounting the reversible value at standard conditions, and this constant block is for this value RT by ZF. We are using it constant because we already defined these values in our .m file, so that's why we are using it as a variable. No worries, we gave these values in that PDF which is shared by you.
So first you build these variables, then we will create a .m file, and there you can take the values from your table, parameter table. Then you run the .m file, then this will be updated. Okay. So first you build the potential by potential blocks.
Or one thing you can do, you can directly use the values for these variables in Simulink model itself. Sir? Can I mention the name of every block?
Variable you carefully note down, capital, small. We'll define them in the .m file.
Okay. So first of all, this one is a constant block. This one? PH. This is a constant block because we have defined the value already in that .m file. If you can, you want to use the constant value, then you can just import the constant block and put 1 e raised to power 6. Here, implement. Okay, sir.
For timing you use P underscore H2.
Next is PO2.
Pressure of oxygen.
We
So if you see the right side, that's what we are going to implement. The open circuit voltage expression that is exactly replicated in Simulink. The same variables also used. Time you need not to open constant block. Once you open one, you can copy paste to save time. And then after PS2 there will be a GAN block. That GAN is 1 by, so basically the denominator of this function 1 divided by P underscore H2O, partial pressure of water.
This is square root SQRT.
Can you double click?
Yes, sir.
Double click. So this is a square root block. If you double click search and type S small QRT, it will give you that square root function and you can add here. So it's a square root of partial pressure of oxygen. So are you everyone getting the components, right? Okay.
Product.
Then as you see in the equation, we are multiplying. So again you just double click and search product. You will get a product block. The same product also you can use the next time. So copy and paste, 2 product block we require. Any question?
No, no, this is the logarithm.
And after the product you will use a basically you search math function. Once you get the math function, you scroll down that, then search this logarithm function. Are you getting, ma'am? Opening. Okay. Sir, are you getting? Huh? You can. So basically you save the model first, otherwise if your laptop doesn't have charge and you did everything, it will be no use. So first save your model as a test model, then keep on doing.
After 2. Okay, sir.
Are you getting? Done? How many people have done so far? This thing. So basically we are using constant block, product block, some math functions and a summation block. So that's how we complete the formula for open circuit voltage. And this is
a go-to block.
this is called a go-to block. Double click. So if you double click search, you will find go-to, and in the tag visibility you put global. Okay, because we will use that value for other purpose, so we are just tagging the variable B open circuit. All these parameter values we will define after we build this. If you are done, let me know. We will go to the next block. So basically in the next block you build below this, so that whoever doesn't completed, they will still follow. This continuous you put near to that so that the space. Scroll down, it will scroll down. So see, some of the block we are using from the previous potential, so no need to again search. Fit to zoom, fit to view. Yeah, that's. Can you put fit to view?
Yeah, which one, sir?
Fit to view. So in the first potential calculation, any doubt? 1.2. Yeah. So that is the standard. What is that?
Reversible standard value.
Reversible voltage at standard temperature and pressure.
This one.
1.2 is a constant.
We have equation for that also, but for the time being we are using the exact value. But if we want to calculate this value at any temperature, we can have the equation for that.
Microphone में सुनना चाहिए. Recording चल रहा है. You hold it if you don't.
Yes.
Hold it. So all of you got? Any question? Backside? Got? Then we will go to the calculation of
Activation potential. Activation over potential.
which equation we are using?
This one.
Yeah. So we are now calculating the activation potential over potential using this function. Which equation? Can you just highlight that? This is the next equation we are going to implement. You can do alpha f inside. Yeah.
Yes, sir. Okay.
Please raise your hand. We will help you if you are stuck somewhere. Yeah. We'll put all the parameters together. That's why we gave the parameter. If you want to use anything, so we can show. .m file together. But first, how to build that we want to teach. Then at a time we'll show the .m. You can copy paste. Are you getting the model, everyone? Okay, you can start building the second part. We are building that highlighted equation. All good? Okay. If you have, can you put the upper block as yes,
sir.
Color. Don't put subsystem, just a color. A sin h. Can you open that sine hyperbolic function?
This is basically inverse of sine hyperbolic.
So you have to type actually trigonometric function. In that you have to select a sin h function. Build, you finish. First one? Yeah, done. Second See your document, page number 3. So if you have the PDF, you can see from that page number 3, highlighted equation we are implementing. Select and drag it, it will be bigger. So that is anode over potential and cathode over potential.
Yes, sir.
So next we are building anode and cathode over potential together, and then we will add them to get the total
Activation over potential.
activation over potential. If you have done, you can, are you following the second one? So this I, whatever you are seeing, it's a from block. So we'll show you where to measure that current. So that current will go and give you calculation of this over potential. So the input, whatever C, is a from block, that is takes current measurement. Okay. Are you getting, all of you? Backside? Are you getting? You can come front if you are not able to see. Okay. I know this is simple thing, but better to have hands on one time so that you can better understand these equations. Okay. Particular important thing is here the unit of each parameter. That has to be proper, otherwise you will not get the actual voltage unit. So the top one is the anode, and this I naught underscore A is A denotes anode, and below the copy of the top one is a cathode.
Anode and cathode. In above one, we are using here alpha A for anodic charge transfer coefficient. In down one, we are using alpha C, cathodic charge transfer coefficient. In above one, we are using exchange current density of anode, and similarly in down one, we are using an exchange current density for cathode. Apart from that, everything is same.
I think the top one everybody completed, right? Everyone? Okay, then if just yeah, if you see there is a summation of 2 over potential. One is for anode, one is for cathode. Okay.
So basically here we are getting the current from our circuit itself. After that we are dividing that current with the area to getting the current density, because while we have to calculate the activation over potential, we use current density, not use the directly current. Please note this thing, because this will create an error. Next thing is current density, exchange current density for anode. Here is I naught A, and is it multiplied by 2, like in this equation 2 I naught A n. Here we implement the same thing. After that we divide our current density with the exchange current density into 2. Then we take inverse sine hyperbolic of this term, and then in the end we multiply this term with universal gas constant multiplied by temperature in Kelvin. We use the value as per the totem file. Here alpha is the charge transfer coefficient for anode, and F is the Faraday constant, which is equal to 96485. So this calculation we performed for the anode itself. Now next one is for cathode. The only change in between the anode and cathode is the charge transfer coefficient for cathode, which is alpha C, and next one is I node C, which is exchange current density for cathode. Apart from that, all things remain same. We are using the same current in both cases, and area is equal to 290 centimeter in both cases. And at the end, we will find the summation of these two to get the net concentration over potential. No, ma'am. It is a divide block. Yes, ma'am.
Current density is equal to current divided by area.
Like as you can see here, the green one, here we have divide. So that's why in this block, this thing is multiplied and this is divide. This is a divide block.
See your PDF, the first equation is our output. The total activation over potential is the sum of anode plus cathode. That's what we are doing as the output from this calculation. All are getting? Any question?
Also one thing, some literature mentioned that we can easily neglect the cathodic over potential in some cases, but for the time being we are considering it to make more precise model, because this value is lesser than that, so that's why we can easily neglect this.
How many of you have done so far? Any question? Feel free to ask. Yeah, sure. I'm just asking, anywhere anyone stuck, let me know.
Where? Yes, ma'am. Yes, ma'am. This one. This is current. That's why we are dividing it by area to getting the current density. Actually, we are getting current density here. This one. This is the current density.
Small I is a confusion, I know, but that small I in the numerator is actually the current density, not current. That's why measured current divided by area become the small I. Okay.
It is represented by small I in literature also.
So
and
please note here, generally in electrical we small I we assume current, but here in this equation we are representing as a current density. Okay. If you have done, we'll have a short tea break, then we'll continue the rest equations and finish the model. We'll have 10 minutes break. If you have done it, you can proceed for tea arranged in the next room.
Yes, ma'am.
Hello, hello. Mic check, mic check.
so let's start rest of the model. And okay, so till now everybody built, or any question first? Let me ask you. So some students have issue because they didn't use MATLAB, so we put our students to help them. Apart from that, anyone? So equations are clear and modeling also clear, right? Only the things are the left is the what is the value of those parameters. We'll discuss that after we finish this. So we'll go to the next part. Over to you.
So I hope you all of have made these two models. So I hope all of you have done with these models. Shall we proceed? So now we have these two potentials, open circuit and concentration. Not concentration, actually it is activation. So as literature proposes that we can easily neglect the concentration losses when we are operating below 3 ampere per centimeter square. So here we doesn't account the concentration losses for this case. No ma'am, V concentration. This is V act. First of all, we calculated here V open circuit.
Which one you change from concentration to activation? They are asking that. The
Yes, ma'am,
second
this is
one.
activation only. Yes, ma'am. Okay, sir. So now we have the values for open circuit voltage and activation voltage. So we have first go to block here. So from this go to block we can directly by swapping or just by typing manually from, we can get this from block here. Like just type from, and they ask for, it asks for go to tag, or just we have to write, which you have defined for that, UOC cell, or it is created. Am I clear? Next we have to do similar for activation potential, or we can do one thing, just by swapping it we can get the activation potential from block for that. So now we have to find the summation for these two potentials. So we can here, I think I have not put. Basically here we are just accounting the cell voltage equation, which says that V cell is equal to V ohmic plus V activation plus V open circuit or reversible plus V concentration. We are trying to implement that only. Ohmic losses are accounting in the circuit itself, so we have to find only activation and open circuit voltage. So now we write sum, we get this sum block. And now we have to create a go to block. just write U cell. U cell or V cell, whatever you want. (80) number of cells in series. So we have created this from block from this go to and multiplied by number of cells to get the actual voltage. So now search for product. And now create one more go to block. And name it as VTH, threshold voltage.
All of you reach to this point?
Done.
Okay. Students? Okay.
Now we will go towards circuit construction. First of all, we have to search controlled voltage source. And now create from block from this go to and just give the control signal to controlled voltage source. I hope it is visible. No ma'am, we will define from .m file itself. Or if you want, you can give 0.2. And sir, we have to compare with our static electrical models. R underscore ohmic underscore PEM. PEM stands for proton electron membrane. This one.
So all of you please carefully write the variable names. It is R underscore ohmic underscore PEM.
So now search for voltage measurement block. Now connect this voltage measurement block with resistance like shown in like shown on the screen. Please connect the voltmeter with the resistance. Now create one go to and one display. Yes, sir. Just I will construct and make it separate. Just one moment.
So all of you will be given a feedback form, so you can fill that and submit.
So name this go to as Viomic. And also search for current measurement. One more go to. And name it as I. Like in activation potential calculation, we define that variable I. So from this circuit, we are calculating that value.
So backside, sir. Are you getting it? Okay. You? Oh, okay, okay, okay. So this is basically a dynamic equivalent model of electrolyzer. But while modeling the potentials, we also included the electrochemical reactions. Of course, we are not putting the chemical equations directly, but we are designing or in terms of a over potential that is calculated from the measured current, measured input current, you can say. And all the PDF you are given, all these expressions are shown there. And this is a simple electrical model. As you will complete today, so what we will do tomorrow, if you see, we are connected this to a constant DC voltage. Now in reality that DC voltage will not be a constant, it will be the output of a DC-DC converter. So that DC-DC converter along with the controller with this load tomorrow will show. So let's complete this today totally so that you can use this model tomorrow.
Yes, sir.
Which bracket? No, that thing might be the version difference, MATLAB version difference. Global you can put. But for you, we are not creating subsystems, so everything is here. So global basically if you deal with multiple subsystem and variables of one subsystem you use in other. That's why if you put local, then it will not be recognized in other subsystem. But as you have everything built on single canvas here, so local is same as global, no need of issue. But basically for safe side, tomorrow let's say when we build other subsystem, we put global so that it will be recognized everywhere. All good? Are you getting, ma'am? Sir, are you getting model? Okay. So now we are going to show you the parameter file, which will either you can write down. I think it is better we send you this. You download and open it your MATLAB, run this, and then you will able to run your model. So can you email me this .m file?
Sir, I think it is in the drive. This .m file is in the drive link we have.
Can you open that different type?
Yes, sir, because we have time.
Time is there, no?
And also I put one tutorial problem in that.
They can try.
Yes, sir.
First let me
Because if they
can you
not,
open this? Okay. So this right side co-pilot you will do. Black background, white background can come or it will not be there. So what you are doing?
background just.
Okay, fine. Close it. Okay. Okay, so this is all of you. You have some time now. I want everyone to type it. Better is like not that much long. Just the equations you understand how to type. Okay. Can you start from beginning? Or it's starting from here?
Yes, sir.
So basically you have to type from line number 58 to 80. Okay. Do you have the option to zoom? Or maybe in a notepad or something, Word file you put where white background we can see. No, here also is black. Leave it. Open the .m file.
But I think here it is more to visible. Size is
No, they cannot recognize. It will again show the error. So is it visible, right? I'll take a photo and put in the WhatsApp. In the .m file.
Sir, I am using black theme. I think it is not
No, you open that now.
I can speak that values. I can announce that value.
So it is visible to all of you? View. Top, view.
This one. Okay.
Fine. Fine. First you line first for 10 lines, then I will scroll it down and zoom it again.
Don't have to just green color things. These are comments only.
It's okay. Is it visible now? We start with line number 58, values for electrochemical. No, wait. Okay. Visible backside? Huh? Visible, okay. Please write them. Line number 58 to 80. And each line definition is written side to that line. What we are doing.
integrate.
बैकग्राउंड चेंज करने का ट्राई कर सकता है.
अभी
बैकग्राउंड कलर.
वाइट है
हाँ.
यार, वहाँ पे सब कुछ शो होगा. थीम चेंज करनी पड़ेगी ना. ब्लैक बैकग्राउंड से अच्छा नहीं लग रहा.
ओके.
वाइट पे रिफ्लेक्ट कर रहा था तो वाइट ब्लैक करके ले गए. This one, anodic charge transfer coefficient and cathodic charge transfer coefficient. This is just a comment, definition for that. This is alpha, it is the summation of alpha A plus alpha C.
all of you completed .m file or any question? Just save it. Done. Done. You can save the .m file and save in a folder or something. Tomorrow also we will use this. Don't forget to save. Once you save it, if you have written it correctly, you can run this .m file once. Can you show where to run? No, on the top, home. Editor. So in the editor tab, you run this .m file. In the workspace, all these values will be saved. After you successfully run this, then you run your model and see it is properly running or not. Check once. If it is not running, then it is not recognizing some variable. Put side by side. Some people are still typing .m file. Yes. Line number.
Just not focus on timing. We are not using here this much.
Till when we are using, you keep that. So everyone .m file compiled?
Basically, R electrical is for the R interface that we have neglected in the equations.
Anybody facing issues in .m file? Sir, all good? Okay, after this, can you run your model? The developed model, can you run? Running .m? Okay. .m file? Okay. Just open it, somebody is using.
.m file?
No, model. R omiki did you define?
Yes.
No, I saw. Which one? Line number is
7.
So line number 7 you can type. Yeah, that's what I want you to test. Which parameter you are facing issue. You want to see model? Can you put side by side this and that? Model which part? Electrical equivalent? Just right side, you zoom it.
This one?
No, right side of the. Visible? Okay. So in another 5 minutes we will close, so let me know if we have done. Which one? Alpha is not defined?
It is defined.
Can you tell the line number?
Line number 70 and 71.
You might have done some typos in the variable declaration.
Alpha A is equal to 0.8 and alpha C is equal to 0.25.
Line 70 and 71. Yeah, that's why I told you to build, because that is important. So now whatever you define in .m, same you can copy and paste in, put your model. Are you done? Okay. .m file working? Model? Please check both .m file and model are working. So today's lecture slides and this tutorial I'll update in the shared drive, whatever I said yesterday, so you can go through. So tomorrow again hands-on will open this model and connect with a DC-DC converter. Okay. Which one? One 192. In the model you are saying? Oh, this port number, how they give, they are asking. Can you double click? No, DC input port number. Can you tell which is the library? It's a signal port, sorry, can you double, it's a connection port. Search in connection port. But here he directly took from, so did you find that connection port?
You can directly put voltage source here between these two ports. Connect positive side.
No, let them do that, because tomorrow we'll use this subsystem again. So connection port, you name it 1 for positive, 2 for negative. Okay. All good? Display? Yes.
Just display.
Display,
Right,
just
display.
search display. Can you tell the values?
For which potential you are asking?
Which one? Current, voltage, which one you want to see? Off means which one? Current? Can you just, this one, see the, which one?
This one, 1.593.
Okay, fine. Anyone want to test?
Just one thing, what is the input supply you gave? Input supply
Input.
across these two terminals?
What is the voltage you gave? No, it is a DC voltage, right?
3 volt for cell and 262 for stack.
Did you tell that?
Yes, sir. And it is provided in .m files.
So this is set at the output actually. So connect that, copy that and connect inside itself for time being. DC supply we are connecting now.
It is by default value.
No, we'll see now how much is.
Just do one thing, import one DC voltage source.
How much voltage you are giving?
This
So
is
here depends, you are designing a cell or you are designing a stack. So if you are designing a cell, then you have to give a cell level input. If you are designing a stack, you have to give stack level input. So for firstly, what you want to see? So
we have to design for cell,
basic
basic one.
So cell voltage is
Just give
basically
3 volt.
3 volt we gave.
Yes, ma'am. This one is V ohmic. Close this resistance. This one, ma'am. In electrical model, we have ohmic losses in a parallel branch. So that's why we are adding them in a threshold value itself. But now we are implementing in a series itself. So that's why we didn't have to add here, because overall our KVL should satisfy. We have go to here.
So if you remember the equation, V cell is equal to sum of all potential, right? So V cell is the input DC is equal to B ohmic plus all other over potentials. So all over potentials we model it as a control voltage source plus B ohmic equal to V cell. Understood? So the left side voltage source, if you see it is a control voltage source. So that control signal is the summation. Can you show which one? U cell, right? That is the summation of two potential, and after these two potential you are left with ohmic. So these two potential plus ohmic is equal to V cell. Get it? For all model worked, model run. Okay, if you have, so we'll close now. So hopefully you can practice it
Sir,
today.
1 minute.
Yeah.
Previously we are not considering this transfer function block. Like in our electrical model we have a capacitance. So here to represent that tau, time constant RC, we are having this value because our electrolyzer has some capacitance effect in inbuilt double layer capacitance. Due to that inbuilt double layer capacitance, that's why we have this transfer function block here. We can replace it by unit delay function, or in simulation if we want to ignore that we can ignore, but ultimately it can causes the algebraic loop error in our simulation. So for that's why we have to consider it also.
The double layer capacitance effect in a electrolyzer. So if you see the slides of an actual electrolyzer cell, so that is, you can see what is the double layer capacitance, and that effect we model it in terms of a first order transfer function to give some dynamics. Okay. Okay, so you can save your .m file model, and we are closing our session today, day 2. Hopefully you got some idea about electrolyzer basic principles, DC-DC converters and controllers, and some hands-on modeling for the electrolyzers. Okay, so we'll resume again tomorrow, same time, same place. Okay, see you. Thank you. Good night.
One thing more, in shared PDF file it has some tutorial, one tutorial problem. Please try to do it. Thank you.